In this lecture, we will continue our discussion of nuclear chemistry and conclude that portion of the material in the class. So in section 2, we're going to discuss the kinetics of radioactive decay. Radioisotopes can be used to determine the ages of certain objects, as I assume most of you have seen in like a TV show or something where they use carbon-14. Okay. The ratio between carbon-14 and carbon-12 is a constant ratio in living organisms because we're constantly taking in carbon from the environment to remain alive. Right? But once an organism dies, the amount of carbon-14 in it starts to decrease, and it decays to form nitrogen-14. Okay, since carbon-14 decays at a predictable rate, right, it's always constant, you can measure the amount of time since something has died by measuring the amount of carbon-14, that ratio of carbon-14 to carbon-12 in a sample. The other way this is done, maybe lesser known ways, is potassium-40 and argon-40 ratios, and that's used to determine the age of certain rocks. So it can also be done in rocks for geological time dating. Okay, and so here is an age scale in years and some points on that age scale. Okay, that have been carbon dated. Charcoal from the earliest culture in Hawaii, relatively recent in the past. Linen wrappings from Book of Isaiah and the Dead Sea Scrolls. Okay, that's, I think that's about 2,000 years there. Okay, earliest settlement in Japan, close to 4,000 years, and so forth. So, I think the oldest thing, at least on the oldest thing on this chart here, charcoal from cave sites in France that had extensive cave paintings, and that was close to 16,000 years ago. Right? So in the terms of human history, that's very, very ancient. And how the time is found is by using this equation. You have the time equals 1 over the rate times ln of the activity not over the activity at the time. So let's try a practice problem using this. We have the charred bones of a sloth in a cave in Chile represent the earliest evidence of human presence at the southern tip of South America. A sample of the bone has a specific activity of 5.22 disintegrations per minute per gram of carbon, and the unit's given there. If the carbon-12 to carbon-14 ratio for living organisms results in a specific activity of 15.3 disintegrations per minute per gram, how old are the bones? And the T1/2 of carbon-14 is 5,730 years. Okay, so we're using that equation that we just saw, but to first part of this, so let's just write out that equation that we're going to need to use, and that's going to be the time is going to equal 1 over k times ln of activity naught times over activity at time t. Okay. So that's going to be our equation. We don't know what k is, though, so that's what we're going to have to find out. So that's where we get use the half-life equation. 1/2 equals ln of 2 over k. We solve for k, so k is going to be equal to ln of 2 over t1/2. So 0.693 over 5,730 years. That equals 1.21 times 10 to the minus 4 per year. Okay, so that's K. So now we can plug in the values, all the values, other values that we were given for activities. So time is going to be equal to 1 over k, which is 1.21 times 10 to the minus 4 per year, times ln of activity is 15.3 at the start, disintegrations per minute per gram, and in that sample that we had, that was 5.22, so considerably less disintegrations per minute per gram. Okay. So when you do that math, the time is approximately 8,900 years. Okay. So moving to the third section of chapter 24, this is nuclear transmutation. These are induced changes in nuclei. So nuclear transmutation is the induced change, conversion of a nucleus of one element into the nucleus of another element. It's achieved by high energy bombardment of nuclei in a particle accelerator. So in the case here, we have a nitrogen-14. If we launch an alpha particle at it in the accelerator, a transmutation that can occur would be the creation of a proton plus the transmutation now that nitrogen-14 has captured one proton and a total of 3 mass units to move to oxygen-17. Right. These reactions can be described using specific shorthand notation. Reactant nucleus, particle in, particle out, and product nucleus. So in the shorthand, this is written as N14, alpha particle in, proton out, and oxygen-17 is the product nucleus. And this is just an example of a linear accelerator where you have a proton source. In this case, it's bombarding protons on the target, alternating voltages, so that shoots the proton forward, right? Protons would be attracted to negative charges, and repelled by positive. So you kind of just alternate these, switch them between being positive and negative. So it draws that proton along and speeds it up and fires it into the target. Okay. There's also cyclotrons where they're circular accelerators. These are maybe a little bit harder to kind of visually understand. But again, they have alternating sources on it. So you flip the sign of these two plates, whether they're positive or negative, and that'll spin that proton get it going very, very quickly until it reaches the end here of the chamber where it is just shot out into the target. And here are some formations of some transuranium nuclides. So those that are larger than uranium and thus not found naturally, are man-made. Okay. Right. A lot of them, or at least these two, involve plutonium, and you can take some that are man-made. These two products here, and make even bigger products still. Okay, so that's kind of how that works. And you'll notice that in the larger ones especially, the half-life becomes very, very small on these. They're very unstable. They last, a half-life of hours to minutes to even sometimes seconds I believe this is Lawrencium, named for Lawrencium, named for Lawrence Livermore Laboratory, I believe, and I believe this is Americium and Curium. I don't recall the names of these. Just don't really, in my line of work, I don't really deal with these, but they're all synthetic and man-made. Moving to the fourth section of chapter 24, this is talking about the effects of nuclear radiation on matter and ionization. Okay, radioactive emissions collide with surrounding matter, and depending on the energies of these collisions, they can dislodge electrons, and that causes ionization. Each event like this produces a cation and a free electron. Okay, the number of cation electron pairs is directly related to the energy of the incoming ionizing radiation. Ionizing radiation thus has a destructive effect on living tissue, and the danger of particular radionucleotides depends on three things: the type of radiation it's releasing, the half-life it has, because that tells you, in a sense, how much and how fast it's decaying in radiation it's putting out, and its biological behavior. Where in the cell will this radioactive element go, or where in the body will it travel to? Okay, and the real danger is this electron, when released, it can become very reactive and create things like hydrogen peroxide, or hydroxide anion, or hydrogen plus ion, neutral hydroxide, which all can then become reactive to biomolecules in the cell. And the one that's really dangerous when it gets damaged by some of these really reactive species is DNA. The unit of radiation for energy absorption is called a gray, and that's abbreviated as capital G sub Y. And it equals 1 joule of energy absorbed per kilogram of body tissue. Okay. The rad is more widely used. 1 rad equals 0.01 joules per kilogram, or 0.01 gray. Okay. And then there's also the rem, and this is the unit of radiation dosage equivalent to a given amount of tissue damage in a human. So this one is probably the one that's hardest to really understand. Okay. So the number of REMs equals the number of rads times RBE, and the RBE is the relative biological effectiveness factor that the REM allows us to assess actual tissue damage by taking into account, 1, the strength of radiation, the exposure time, 2, and 3, the type of tissue. Okay, so REM is probably the most accurate or best description of it, but in terms of our class, it'd be the hardest for us to have you calculate. So I'm not gonna have you do that. Okay. All right. The effect of radiation on living tissue depends on both the penetrating power and the ionizing ability of the radiation. So penetrating power is inversely related to the mass, charge, and energy of the emission. And if you look at the 3 different types of radiation we primarily have talked about have been alpha particles, beta particles, and gamma rays. And you'll see that alpha particles really don't penetrate very far. If you're looking at a liquid here, this is liquid water, a test tube, they're 0.03 millimeters, and beta particles really aren't that much further, 2 millimeters. Okay, gamma rays can go up to 10 centimeters through that water. Right, so the type of shielding you would need to protect yourself from these varies. For an alpha particle, a simple piece of paper is enough. And and really, like, they just kind of bounce off your skin. If you're working with an alpha particle, it's not going to really break your skin or penetrate your skin and go deep into any tissue at all. The problem with things like plutonium's an alpha emitter. And the reason why it's so poisonous and dangerous is that if it's ingested, it's in your body, then those alpha particles, then they can do some damage because they're right next to your internal organs and tissues. Okay, beta particles, those are the electrons, and they can be stopped by a single, a small piece of plexiglass is enough to stop them. And then finally, gamma rays, you need a fairly thick amount of lead shielding to be able to shield effectively from gamma rays. The interaction of this ionizing radiation with molecules causes loss of electrons from a bond or a lone pair. And this results in the formation of what are known as free radicals. Okay, there's single molecules with single electrons that are very, very reactive. Okay. Free radicals, they're unstable, extremely reactive. So in this case, if water reacted with a gamma particle and lost an electron, it'd be H2O plus, H2O dot plus. The dot indicates an unpaired electron. Okay. That then can react with another water molecule to form H3O plus, hydronium ion, and an OH minus, a hydroxide anion. Okay. All right. Double bonds in membrane lipids are very susceptible to attack by these free radicals. So membrane lipids are a potential place where these radicals can attack. Okay. There are several natural sources of background radiation. There's what's known as cosmic radiation, and that increases as you go to higher altitudes because there's less atmosphere protecting you at higher altitudes. Radon is a radioactive product of uranium and thorium decay in the soil, and radon contributes to about 15% of annual lung cancer deaths, which is a huge number, right? So it's the second leading cause of lung cancer behind smoking. Radioactive potassium-40 is present in water and various food sources. So anything with potassium in it naturally has some potassium-40 in it. And radioactive C14 occurs in all carbon, but it's also in atmospheric CO2. Okay. So you're breathing some of that in with every breath. So typical radiation doses are shown here in millirem per year. So from cosmic radiation, we get about 30 to 50 millirem per year. Radiation from the ground, depending on what type of house you live in, the amount varies a little bit, but you can see that it's in general a little bit higher. You're getting a little bit higher dose from this source than the cosmic radiation. Radiation from the air, if you're outdoors, it's about 20 millirem per year, but inside it can be, again, much higher. Internal radiation from minerals in the tap water or daily intake of food is about 40 millirem per year. Okay, so these are all sort of similar in scale to each other, these sources of radiation. Right, what about outside sources, that you can control exposure to? Things like medical sources like X-rays, the values here now are given in rad instead of rem, which makes it kind of hard to compare. Other sources, if you go on a flight, that's about 1 millirem for a 4-hour flight. Nuclear testing, it's estimated that you get about somewhere less than 4 millirem per year from previous nuclear testing on the planet. So the total average value from artificial and natural sources adds up to about 100 to 200 millirem per year. This map shows the radon distribution in the country, and you can see that it's fairly high here in Denver. Just kind of a geological anomaly, I guess, there, having to do with, again, the decay from uranium and thorium in the soil. So places that have higher deposits of those minerals in the soil show a higher amount. And you can see that here as well. So very high ranges here. So, and overall sort of higher in this west, Midwest area and along the mountains here in the east. There are two models of radiation risk. Nobody's really sure which one is the more accurate model. Linear response, that model proposes that radiation effects accumulate over time regardless of dose. And the S-shaped response implies that there's really a threshold above which effects are more significant. So lower doses, not really that big of a deal. Until you reach a higher dose, then the significant risk starts to occur. This figure or table here shows the effects of a single dose on whole body. If you have a small dose like 5 to 20 rem, possible late effect, possible chromosomal aberrations in the DNA. 20 to 100, now you get temporary reduction in white blood cells. 50 plus rem dose, it causes temporary sterility in men. Okay? And so this is a single dose, right? That's 50 rem. And remember that you get something like 100 to 200 rem per year background. But if you can take that's spread out over a whole year period. If you take half to a quarter of that and just do it all at once, that would be enough to cause this temporary sterility in men. 100 to 200 rem, that causes mild radiation sickness, which would include vomiting, diarrhea, tiredness for a few hours, and make you feel pretty bad. 300 plus, that's permanent sterility in women that would cause. 500 would be serious radiation sickness, and this is where we get into how lethal the dose would be. And this is estimated that if you had for 500 rem dose, you'd be about 50 to 70% of the population would die. And the number of days that would take would be about 30. 400 to 1,000, that's where you get that acute illness with some early deaths from that. Okay, and that 60 to 95% of the population that was exposed to that would die. And something like 3,000 rem, that's death in hours to days. Okay, so that's not very cheery, is it? Let's talk about some applications of radioisotopes. See if that can cheer us up here. Isotopes of an element exhibit very similar chemical and physical behaviors. Small amount of radioactive isotope mixed with the stable isotope will undergo the same chemical reactions and can act as a tracer. So radioactive tracers are used to study reaction pathways, particularly in biochemistry, that they've been used quite extensively in the past, to track physiological functions like breathing, where oxygen goes when you're breathing, that sort of thing, to trace material flow, identify components of a substance from a very small sample, and to diagnose a wide variety of medical conditions. Right, so here we have pictures of thyroid gland, and we're doing, in these pictures, they're doing iodine 131 scan on the left shows an asymmetric image that is indicative of disease, and the 99, man, I can't remember off the top of my head what TC is, another radioactive nucleotide. That scan of a healthy thyroid is on the right. So the one's asymmetric, and the other is more symmetric. So using radioactive nuclei to image things has been used widely for years. Right. Let's try a practice question. Iodine 123 is used to study thyroid gland function. The radioactive isotope breaks down via alpha decay, a first-order process, with a half-life of 13.1 hours. Write the balanced equation for this reaction, and what is the rate constant for this process? So we can write our chemical or nuclear reaction that's occurring here. And we have iodine 123. Iodine has an atomic number of 53. And it decays via an alpha particle. So we know that the alpha particle has a mass number of 4, and it has 2 protons. So we know 123 has decreased by 4, so that's 119 mass number. And we know 53 has decreased by 2, so that goes to 51. And element 51 is antimony, Sb. Okay, so there's our reaction, or nuclear reaction, yeah. Second part, what is the rate constant for this process? So anytime you're asked for a rate constant, it means you've probably been given a half-life or can look the half-life up. So we just set up our equation. Half-life equals ln of 2 over k. That's the rate constant. We can just rearrange that now. K equals ln of 2 over half-life. So ln of 2 again is 0.693, and half-life here is 13.1 hours. So this equals 0.053 hours to the minus 1, or 1 over hours. Okay, so that would be our rate constant. Here's some radioisotopes that are used as tracers in medicinal diagnosis. Ones that there's none that I really have much experience with myself pointing out. I have noticed that in the past, in the research I do, they would actually give C14 CO2 to breathe into patients, because one of the pathways that and C14 glycine as well, because they're studying the glycine cleavage enzyme pathway, and that they could actually trace through to different molecules and follow that through actually, giving glycine and then counting the amount of C14 that's coming out in the carbon dioxide that the patients were breathing out. A PET scan is something, positron emission topology. Those scans show brain activity in this picture. A normal person is on the left, and then a patient with Alzheimer's disease is shown on the right. And you can see that they're definitely a drastic difference on the PET scan between a normal person and a patient with Alzheimer's disease. Right, so those isotopes that they give you in PET scans are sort of emitting positrons. Other applications of ionizing radiation: cancer cells divide more rapidly than normal cells, and therefore are more susceptible to radiation that can interfere with DNA and cell division. So that's I don't know if that therapy is not used quite as much as it used to be in the past, but it's still used, especially now with the more targeted ability to target the radiation to only the cancer. That really helps lessen the side effects it has. It used to be that if you had radiation treatment, you'd like have all your hair fall out, and you could become sterile, and it really took a toll on you. But I think it's a little bit better now with the advanced instrumentation. Okay. You can destroy microbes with it. You can sterilize things with it. So food, the sterilization of food by using ionizing radiation will increase its shelf life, and that kills the microorganisms like the bacteria and fungi on it that cause rotting and spoilage. It can be used for insect control. I've never really heard of that exactly, how that works, but according to the book, it's done. And you can use it for power, for spacecraft instruments, or nuclear power at ships at sea, submarines, things like that. This picture in the book is just showing you the difference between something that was non-irradiated and something that was, potatoes in this case. And the ones that were irradiated have lasted longer. There were some important discoveries in nuclear chemistry by women, right? Marie Curie, I think most of you have heard of her. She actually discovered radioactivity in the late 1800s. Irene Curie discovered artificial radioactivity and helped identify the neutron in the 1920s. And then Lisa Meitner discovered and explained nuclear fission in 1930. And nuclear fission became very, very important in the world soon after that. This is just a picture of Pierre and Marie Curie. They worked as a team discovering radioactivity, and it was very beneficial, I think, to their notoriety, their careers. But it was also very tragic because their continued working with radioactive materials, and this was, they discovered it. It was before anyone really understood it fully and understood the dangers as well, led to their premature deaths. Okay. What they were looking at was pitchblende, which is the mineral uranite, which is uranium with 2 oxygens on it. Okay. And other things like the torbanite, which is a more complex ion with that uranite in it. Right, so they took this pitchblende and they were isolating out the uranium from that. So that's just one of the radioactive things they were working on. Also discovered thorium. And so after discovering thorium, Marie Curie said something like, "The fact is very remarkable and leads to the belief that these minerals may contain an element which is much more active than uranium." Also discovered radium and polonium, okay. 2 other radioactive substances. Okay. Lisa Meitner, along with Otto Hahn, really were the first to come up with this idea of nuclear fission. And what nuclear fission is, it involves the splitting of a larger nuclei into two smaller nuclei. So using neutron bombardment, you can start the process of this atom splitting or nucleus splitting. All right, fission releases energy and generates more high energy neutrons, and so those high energy neutrons that are generated from that first split can then go on to split other nuclei further. So you're creating a chain reaction by doing this. So every nuclei that's split throws out more neutrons, and thus you get a chain reaction. The mass required to achieve this is called the critical mass. The energy from nuclear fission can be harnessed and converted into other forms of energy. And that's the concept behind nuclear power plants. Okay. This is beyond the scope of the class, but the nuclear binding energy, the mass of the nucleus is less than the combined masses of its nucleons. Okay, and so the mass will always decrease when the nucleons form a nucleus, and the lost mass is released as energy. Energy is required to break a nucleus into individual nucleons, and the nuclear binding energy is the energy required to break 1 mole of nuclei into individual nucleons. So that binding energy is going to be expressed here in terms of electron volts, which is kind of a little bit different because usually we're used to expressing energy in joules. But if we took nucleus plus the nuclear binding energy is the number of nucleons. So at 1 atomic mass unit, that would be 931.5 times 10 to the 6 electron volts, or 931.5 mega electron volts. Okay. So a lot of energy. Short story. Long story short, it's a lot of energy. Okay. So here we have the fission of U-235. So uranium-235, that's the one that's fissible. And there's a couple isotopes of uranium, but that's the one that's fissible. So if you bombard it with a neutron, there we go, it will split, and it splits into barium-141 and krypton-92. It also releases 3 neutrons and then a whole lot of energy. So and those 3 neutrons can then go on to split other uranium-235 nuclei. Right, so you get a chain reaction. Here's a different reaction. This is similar to the figure, but now we're making strontium-90 and xenon-143. So, you know, the products you make can be different, right? Right. So the book here, now we're splitting more and more, right? So things like zirconium and tellurium, rubidium and cesium are coming out. Okay. So lots of different products can be made, but what you're doing each time is you're also releasing neutrons, which then can go and split more uranium atoms, causing this amplification each wave and a chain reaction. So the nuclear power plants can harness this energy that's released during this process and use it to create power. And so this is just a picture of a nuclear power plant. So in this power plant, what do they have? Well, they have a reaction core, and this is where you have enriched uranium-235 in what are known as fuel rods. And so the fuel rods will heat up and undergo fission. And they have what are known as control rods that sort of block that fission and slow that fission down. And so there's kind of a play going on with how much fission you want and how much do you want to be blocking it. So the control rods can be raised up and down to control this amount that's visible at a given time. Right? So what you're doing with all this, there's this jacket and core where the fuel rods are, and when the fission is going on, you're heating this fluid up, and that fluid is flowing through a tubing and a heat exchanger in a tank of water, a large body of water. Okay. And then you're transferring that heat to the water heat. Okay. And so the water that's being heated by this process is used you boil it, and then you use that steam that's given off to spin a turbine. That turbine then generates electricity in a generator. Okay, so you're not using the nuclear atoms, this fission, you're not using that energy really directly. You're using that energy to, in a sense, boil water, and then that water turns a turbine and creates electricity. Okay. So it's a fancy way to boil water, but instead of cranking up a bunch of coal or something like that, or gas that you'd have to just keep burning and keep isolating, keep paying for, you just have uranium sitting there and it does the same thing. Okay. That steam then, once it's used to spin the turbine, right, you need to condense that back down to liquid water, and that's where you have the cooling, like a cooling water line for that purpose. So this is a very clean form of energy, right? You don't give off any exhaust. That's when people call nuclear energy clean, that's what they mean. You're not producing any exhaust going out into the environment. What is dirty, however, is the uranium itself, right? You don't want that in the environment. And when the uranium reaches the end of its life and it's been spent and turns into other elements that some of them themselves are radioactive, that is nuclear waste that needs to be disposed of correctly. So that could be potentially very environmentally unfriendly, correct? So that's the downside of nuclear energy. There's a lot of upside to it. It's basically unlimited energy, and it's very clean in terms of like a carbon footprint and environmental impact, as long as there's no accidents. But the chance of an accident occurring is pretty much 100% if you're given a long enough time. This figure just shows another way to look at the nuclear reactor. You have that fluid flowing through it, and you have the uranium and control rods controlling how much fission is going on, how much it's heating up that fluid that goes through there, and then obviously that goes to another place where that is used for the high temperature that creates is used for the purpose of generating power. Okay. Just a look at a present day nuclear reactor. Okay. There are also cooling towers, and they're not really shown in this picture, but that's what you typically think of when you see a nuclear reactor. And those are used to cool, for that cooling water to cool it back down. And that steam coming out of there is just, it's not, radioactive. It's just water vapor steam. Right. What happens? So that's a controlled uranium chain reaction. So you have that under control. But if you don't have control of that chain reaction and it just keeps going, some bad things can happen. And that's what's the principle that's used in nuclear weapons. This was the first nuclear weapon design, And it was very simple. You took two pieces of uranium that were subcritical, so the masses of them, they wouldn't themselves just spontaneously go into fission and create a chain reaction. And you kept them separated in the bomb, and then when you wanted to detonate it, TNT explosive would be ignited, and it would shoot one piece into the other piece. Okay, and then it would become critical mass, and you'd get that uncontrolled chain reaction, creating a large explosion. Okay, because you're letting all that energy out at once. Right? Today's weapons are a lot more advanced and a lot more powerful. They use what was sort of the second design for fission bombs, where you have an implosion that kind of smashes a plutonium sphere on itself and creates an implosion, and that creates the critical mass of the plutonium in fission. You use that to ignite a secondary phase, and the secondary phase is very small molecules, first starting with hydrogen and deuterium, and that's why these are called hydrogen bombs. Okay, you're using a normal old school atomic bomb to start a fusion reaction. So you're using a fission reaction to start a fusion chain reaction that's out of control. Okay. Right, and so the fusion bombs can become very, very powerful. The first atomic bomb dropped on Hiroshima was 15 kilotons. So that cloud was about 12 kilometers high, which is sort of on the scale of Mount Everest. The largest to date hydrogen bomb that was detonated was 50 megatons. So we're talking about 15 kilotons, something that's almost 3,000 times bigger, 50 megatons. Okay. That was exploded in Russia. It was actually scaled down from a 100 megaton design. So if you can imagine that, could have been double the size. Right. The mushroom cloud from this was about 64 kilometers high. So just utterly massive explosion. Right. How nuclear bombs are delivered these days is by ballistic missiles, at least the strategic nuclear weapons. So in a ballistic missile, the missile goes up, and the rocket actually cuts out within the first half of that flight, and it breaks apart, and what it does is it launches the vehicle out, and it's sort of like lobbing a ball. If you've ever kind of lobbed a ball up in football or baseball, something like that, really high into the air, and then it just kind of floats back down to where you intend it to land. So you're not, throwing it directly at its target, but it's going up. And so it goes up basically to space or very close to it. And that vehicle comes out, and then it can deploy up to 6 warheads. So up to 6 warheads can then rain down onto multiple targets. And so once it's up here, and once it's released those, it's very hard to have a defense system to go after these individual warheads. Right, and it can be, these can be launched within minutes of somebody giving the order to do that, and once that happens, they can reach their target, fairly quickly. So something like within a half an hour to an hour, full-scale nuclear war could occur, which is very terrifying to kind of think about. So how many nuclear weapons are there? Thankfully, not as much as there used to be. I think this is sort of the estimate now. Russia and the U.S. both have about 7,000. It's still probably way more than would ever be needed, but it's a policy called mutually assured destruction, which has, at least until so far, has kind of worked, I guess. The other countries, it's estimated they have about 1,000 total combined. Okay. Back in the early to mid 80s, the numbers were substantially higher, with the U.S. having over 60,000 and Russia having close to 40,000, so 100,000 nuclear weapons. That number is just mind-boggling. This figure shows nuclear explosions since 1945, and it's just kind of interesting to see, the locations on the Earth that have had these. The Pacific, South Pacific have had a lot, and they've kind of had to deal with that. These island nations. That's where the U.S. and its allies were testing. Russia was testing, I should say the Soviet Union, because that's what they were called at the time, was testing primarily in Siberia. And then we've had some testing from China as well, and that's in the kind of the outskirts of their territory. So those are the primary regions. And interestingly enough, there at the Nevada test site, there were actually quite a few tests done there. And the exact numbers are shown. 100 atmospheric tests, which is very crazy because you can consider how close Las Vegas is to the testing site, and in other cities as well. You have 100 nuclear tests there in the atmosphere, and then another 900 underground. So most of the testing since 1963 have moved underground. Scattered throughout the rest of the U.S., there are 7 underground tests, and those primarily in the West, between 61 and 73. So this video shows every nuclear explosion since 1945, and it shows it on a map, and it gives either red or blue blips depending on who was doing the nuclear test. And it does it in kind of like a time scale. So you see just how kind of at first the explosions were very rare. They took a long time between them. And then in the height of the testing, it was just like, you hear blips and beeps like so frequently, and it's very crazy just how much nuclear explosions were going on at that time. It was insane. So I recommend watching that video. It just gives you a good understanding on the past. Okay. Fortunately, there is a good use of fusion, not just to make huge explosions, but to actually create reactors to generate energy. And I put these slides together a few years ago, but more recently, just in the past 6 months or so, couple months really, I think, there was that announcement that they've kind of made that first step at nuclear fusion in a reactor. So if that could come in our lifetime, that would be a great thing, because that would be much cleaner. Theoretically, it should be much cleaner energy than even a nuclear fission reactor. You wouldn't have the same sort of waste products being produced in that, at least as far as I know. So, and the amount of energy that could be produced is much greater than a fusion reactor could make. So hopefully something a little bit optimistic to leave you with.